Hello, and welcome to this eSchool Media webcast. My name's Andrew Barber, and I'm a senior contributing editor here at eSchool Media. And I'll be acting as the moderator for today's presentation, which is sponsored by Maplesoft. And over the next hour or so, we're going to explore some of the new technologies that are revolutionizing online education. And in particular, we're going to hear how the University of Waterloo is using online learning tools like Maplesoft's Möbius to develop and administer customized STEM courses to students around the world. But before we get started, let me just take a few moments to explain a couple of things about the console that you're all looking at today. First, we are going to be recording the event. So in a couple of days, we'll send out an email to everyone on this call that contains a link to the recorded event. And you'll also be able to download a PDF of the presentation from that same email. And second, please ask questions. Don't feel as if you have to wait until the end. At any point during the presentation, if you have a question, just type it into that Q&A box on your console and hit the submit button. And I hope we'll have about 10 minutes or so at the end when our speakers can address your questions. We also have a chat function, which you can launch from that blue group chat icon down at the bottom of your screen. And use chat to talk with fellow colleagues in the audience, or to contact me or the eSchool Media team if you have any technical problems during the course of the presentation. But I do have one favor to ask of you. Please don't use the chat function to ask our panelists questions. They're simply not going to have time to look at the group chat while they do their presentations. So if you have a question for them, please use the Q&A panel instead. And it's possible that one of our speakers will use a screen share today. And if that happens, sometimes when we come out of the screen share, the console can get hung up. If that's the case and you're not seeing the slides advancing after that, please just refresh your screen and it should be okay. And with that out of the way, let me tell you about today's speakers. Dr. Steve Farino is the Assistant Dean of Online Studies in the Faculty of Mathematics at the University of Waterloo in Ontario. And Steve is a winner of the university's Distinguished Teaching Award, and he's been heavily involved in online courses since 2010. And our other speaker from the University of Waterloo is Stephen Tosh. Stephen is an instructional digital media developer and part of the team at the university's Center for Extended Learning. And he works with instructors to develop high-quality online courses and courseware in STEM subjects. And most recently, he assisted in the development of the Center for Education in Mathematics and Computing's open resources that used Möbius as one of the primary development tools. And before we turn things over to the University of Waterloo team, though, we're first going to hear from Andrew Rourke, who's the director of the Teaching Solutions Group at Maplesoft. And Andrew speaks regularly at events around the world about Maplesoft's unique solutions and its user-friendly features that support a range of objectives within the academic community. Now, before I hand over the reins to Andrew, I do want to start with two quick poll questions that will help everyone get a sense of where their colleagues' institutions stand right now with respect to online courses. So here's the first question. Where is your institution on the journey of providing online courses to students? And obviously that ranges from people just starting out to those who have the content and know exactly what they need. So take a second to look those over and hit that submit button, and then we will, and I'll move on from there. All right, hopefully you've had a chance to look it all over. I'm going to see what we have in terms of results. And as you can see, we're actually pretty much across the board here, from just starting out at 31% all the way to quite a lot of people, 37% have the content and know the platform that they need. Now, let's move on to the next poll and the final one, and that is getting more specific about online STEM courses. And how many, if you have to estimate, how many STEM courses does your institution offer wholly online? I'm not talking blended courses or hybrid courses that are completely taught online. And you can go from 0 to more than 40. So let's take a look at that. And there you have it. We have a lot of people who are in the early stages of 1 to 0 to 20 perhaps. but we do have about 10% who have more than 40. So that is, I think Andrew Rourke may have some comments about that, but I'm going to just return us now to the beginning, and then now that we have a sense of where the members of the audience stand with respect to online courses, let me get out of the way and hand it over to Andrew Rourke to talk more about the current landscape for online learning. Andrew, welcome. It's a pleasure to have you here today.
Thanks very much, and my thanks to you all for attending this session today. I hope that you'll gain some meaningful information and some good insight from the time that we spend together in this next hour. The three of us are going to approach this topic from three different perspectives, and for my portion, I wanted to share from our point of view as education technology providers and partners in the academic space for over 30 years. By way of a bit of background on the use of history of computing in education, the broad categories would have to include mainframe computers, in which selected departments had access to room-sized machines in order to perform calculations, generally for specialized applications or research projects. Next came the PC revolution and the wide-scale advent of the computer lab. Once the cost and the size of computers made their adoption sensible, computing applications for teaching and learning became available to virtually all students by schools outfitting computer labs for students to be able to access technology on. The continued decrease in both cost and size of computers, as well as their increasing portability, brought about a whole new age, a time in which students began to bring their own devices to school for use both in class as well as at home. Finally, the modern age that we find ourselves in today, where students are accessing the internet and course materials on a whole host of different platforms, from more traditional PCs and laptops to tablets and web-enabled phones. Today, we're well into an environment in which courseware materials are being developed for consumption online, sometimes wholly, sometimes part of a flipped or blended model for on-campus students, while at other times being fully online, either for campus or distance ed students. As part of this movement for education shifting into the online space, there has been exponential growth of courses coming online. In this case, MOOCs offered by the big five providers, but the course distributions have been uneven. This chart shows a topical breakdown from last year across the spectrum of MOOCs, and STEM in total represents less than 20% of the offering. Core math, in particular, represents just over 3.5%. A conclusion that I draw from this data is that, in part, the reason that so few STEM courses have come online is that until this point, faculty and content authors have recognized the challenges and difficulties that lie in being able to create effective, engaging materials that actually hold student attention and lead to positive outcomes. Now, there certainly is recognition that needs to be extended to those faculties that have endeavored to bring STEM courses online already. Nearly 4 years ago, a number of colleagues and I sat in on a workshop at the University of Toronto in which a dozen leading-edge STEM educators from across North America had gathered to showcase how they developed and deployed their STEM courses online. On the way home, we remarked to each other that while the presentations had been enlightening, at the same time, they were also slightly terrifying. Here we had a dozen passionate educators trying to bring STEM courses online, and yet all were doing something different, similar but different. YouTube videos, LMS deployments, pulling in Khan Academy videos, visualizations from tools like GeoGebra, on and on it went. There was no consistent student experience. There was no measurement or analytics. There was no evaluation for pedagogical soundness. There was no live math. There had to be a better way. And we realized that we already had the raw materials to make such a better way come to life. Now, let's look at where the movement for STEM courses going online in the past decade has brought us. The first version of courses coming online, 1.0, was characterized by the simple posting of static documents like PowerPoint slides, Word notes, and existing PDF course materials. Some faculty did try to enter the electronic realm by posting recorded lectures, but typically these were long-form attempts to recreate the lecture experience just in an electronic format. Certainly for STEM courses, courses where students need to be hands-on and interacting with live materials, this was not only pedagogically unsound, but simply unpractical for any hope or measure of success. Online 2.0 saw improvements in that lecture formats were better tailored to student learning styles, rudimentary assessments were incorporated, LMSs were developed to present courses in a more consistent and streamlined way, but fundamentally the course flow was still linear and tried to replicate in-class learning. Today, education has already moved to the edge of Online 3.0, and that's characterized by both a number of features as well as the combination of a number of features that make up the modern online teaching and learning experience. There are many elements that make up Online 3.0, and in designing an online courseware system to meet up with these kind of characteristics, it would have to include things like the ability for students to have access to live math in order for them to be hands-on with the concepts and actually learn by doing. It would have to be integrated with enterprise tools so that students aren't jumping around from platform to platform within the same course. It would need to be flexible enough to be adaptive to student needs both proactively and reactively. It would need to have a modern user interface to keep students engaged. It would need to be portable to meet students on whatever device they need to access it on. It would need to provide analytics in order that the learning process could be managed at the micro level, not just at the macro level. And the list goes on. Now, the students that you have today in your classes are the first generation of true digital natives. They can't remember a time before. That is, before smartphones, before the internet, before Google. They've grown up in a world where information has literally been at their fingertips 24/7. As a result, students have an expectation that their education will be as connected as the rest of their lives. They expect the materials to be engaging, interactive, informationally dense, and highly visual. To be sure, the materials need to be at least as good as what they can find instantly and freely online. In previous generations, students could achieve some level of success by simply knowing lots of information. Today, success is beginning to be defined not by how much stuff you have memorized, but by how they can apply critical thinking to connect different fields of knowledge to find new and novel solutions to problems. So what about the future? Well, we're already seeing the beginnings of mostly non-technical, but still fully accredited online degrees offered to students from anywhere at any time. Eventually, students will be able to choose the correct mix of online versus on-campus that is best suited for their individual learning styles and schedules. The next stage in this evolution will be to allow students to pick courses from various institutions around the world to make up their degree. Now, there definitely are barriers to implementing that type of mix and match approach, but e-education systems can provide the framework for STEM courses to make this type of education possible. The first step on the path towards Online 3.0 education for STEM-based courses is our solution called Möbius. Now, how Möbius fits into the landscape is that e-education materials can be broken down into modularized learning objects. And these objects provide short units of active learning coupled with recall, interactivity, application of the concept, assessment, and evaluation. In short, they cover what I call the 4 E's of education. The first one is exposition, where the concept is presented and explained. Next is exploration, which allows the student to interact and fully explore the concept being presented. Then come exercises to ensure that the student is able to use and apply the concept. And finally, the evaluation, which determines the student's level of understanding. And evaluation can also help to determine or suggest the next best steps in that student's learning process. One of the biggest challenges facing education today, especially for those courses involved in the STEM disciplines, is that tools for learning, exploring, and evaluating have existed. But until now, they've existed as distinct and disconnected tools supplied by various vendors and for a variety of platforms. What Maplesoft has to offer to students, to instructors, to instructional designers, and to administrators is the ability to contain all of these critical tools in one concise environment. And with that bit of context, I'm going to pass to Stephen Farino for some background on the University of Waterloo's online offerings and some of the salient issues relating to digital assets that it had to address.
Thank you for joining the 2 Andrews and the 2 Stephens for this webcast. As you heard, my name is Stephen Farino, and I am the Assistant Dean for Online Studies in the Faculty of Mathematics at the University of Waterloo. The Faculty of Mathematics is unusual, and this figures into some of the areas we've had to pay attention to. Many departments of mathematics tend to be smaller service departments. That's not us. We have almost 7,000 honors undergraduates in mathematics, with roughly 75% of our students in co-op programs where school terms and work terms alternate. We have about 1,000 graduate students and 240 faculty members. Half of our students are international students. We teach hundreds of different courses in a year, and we are also internationally ranked. We now have considerable expertise offering courses online, and this slide indicates a few of our efforts. We currently offer over 50 courses for degree credit that in total enroll several thousand students. Our open courseware is used by about 120,000 people each year. I'd like to spend a while with the questions we've been asking ourselves about teaching mathematics, and indeed any STEM subject online. Though these arise out of our particular circumstances, I suspect some of the questions will resonate with you. For many of us in a classroom, the spread in background preparation, native ability, and interest among students is very large. At Waterloo, we have single calculus courses with over 1,500 students spread across a number of sections. How do we teach to such large numbers and provide adequate remedial and enrichment opportunities? And specifically, how do we provide review and remediation at a time when the student sees the need? Not simply how do we provide review material, but how do we provide review material at 1 o'clock in the morning when the student is working on their assignment and we, or at least I, am not available? And how do we validate that the students have used the material and learned from it? As a former associate dean, I had the opportunity to listen to student frustrations, and they are seriously frustrated about the cost of textbooks. It will come as no surprise that a significant fraction of our students do not purchase a textbook, and so place themselves at a serious disadvantage in learning the course material. So how do we replace textbooks without sacrificing quality? The Faculty of Mathematics already offers about 50 courses online. In building those, we have learned lots of lessons, foremost of which is that this can be a slow, expensive process. At the University of Waterloo, we are fortunate enough to have a production group, the Center for Extended Learning, that does most of the heavy lifting in actually producing the digital assets that make up a course. Subject experts work closely with online learning consultants and developers from CEL. A chronic pain point for us is maintenance. What appears on the surface to be a straightforward fix can take hours in our legacy projects. We now have about 125 firm projects in the pipeline. How do we design, develop, and deploy STEM digital assets in a manner which is efficient in authoring time, efficient in production cost, and efficient in maintainability? Lots of people think reuse is one way to proceed there, and in some sense, reuse seems trivial. Of course, we should be able to reuse digital assets from one course in another course. It turns out to be not so trivial in practice. Different technologies over time, different intellectual property agreements, different voices of authors, different layouts, different notation. Finding a suitable asset to share in a sea of thousands of assets are all obstructions to reuse. So how do we build digital assets that can be easily shared across courses? Indeed, when we say courses, we should keep in mind that those courses may be face-to-face, blended, flipped, or wholly online courses. Our students, their parents, and taxpayers contribute many billions of dollars in aggregate to education. Is it working? What empirical evidence do we have that students are learning? Will they remember how to solve a system of linear equations beyond the exam? And for many of us, better learning is what we are all about. So how do we embed the insights of cognitive science into our teaching? At Waterloo, we lovingly handcrafted our first 40 online courses in various technologies: Flash, video, narrations over LaTeX slides in Camtasia, and HTML. But all had significant drawbacks. Among those drawbacks were problems with maintainability, difficulty in sharing assets between courses, a lack of compliance with accessibility legislation. Not all assets were well designed for mobile devices, but most especially, there was a lack of interactivity and weak analytics. With the experience of many courses and with explicit attention paid to the questions I've raised, and being cognizant of the weaknesses of the digital assets we had already produced, we went looking for software to support the design, development, and deployment of the next generation of interactive STEM digital assets. What we wanted didn't exist, or at least we couldn't find it, even through a public tender process. So we partnered with Maplesoft to build Möbius. Maplesoft already had two crucial pieces of infrastructure in place: a mathematical engine that we could use throughout the undergraduate and graduate curriculum, and assessment capabilities. Pedagogically, we focused on four elements. Exposition. Humans like storytelling. Exposition, mathematical storytelling, is what many of us think of as our primary duty as teachers. And doing exposition well is difficult. We've been at it for a couple of thousand years and haven't discovered any magic formula. I'm convinced, though, that exposition is far from enough. Experimentation. Humans learn by doing. Mathematics is not a spectator sport, so we need the ability to allow students to carry out experiments with mathematical objects. Can we rotate a three-dimensional surface to find local minima? Can we modify parameters of a system and observe changes in the system's behavior? Exercises. Humans rationalize. How often have you heard the line, "I really know this stuff, I just can't do this question or that question"? Being able to ask a mathematically sophisticated question, receive a mathematically sophisticated answer, and give real-time feedback allows the student to be honest with themselves about what they know and what they don't know. If we can repeatedly ask questions in a low-stakes environment, then students can practice and learn at their own speed. Finally, evaluation. Universities and colleges grant degrees and credentials of various kinds. We need to be able to assess the performance of our students, and we need to be able to evaluate their skills. As an administrator, there is another aspect to teaching and learning, being cost-effective. So we need a tool which supports enrichment and remediation and is effective pedagogically, evidence-based, and is efficient in time and money. For this, we need to collect data, and Möbius certainly gives us that opportunity. To show you some of the details of how Möbius is being used at Waterloo, let me turn it over to one of our online developers, Stephen Tosh.
Thanks, Steve. I'm going to jump right into the Möbius system. We'll talk about the general structure of Möbius, the kinds of content you can put into it, and try to give glimpses here and there along the way of how UW is making the most of Möbius to produce effective content efficiently. At the end, I'll discuss some of the strategies we are now implementing or beginning to implement to further improve efficiency and the reuse of content. The Möbius system at its highest level consists of classes and users. Within classes, content is organized into units, and units consist of lessons, which encompass the elements of exposition, experimentation, and exercises, and assignments, which cover evaluation. It is worth noting that a class can be created as the child of another class. This automatically gives the child class access to all the content in the parent class. Again, we'll cover more on how we're using this feature later at UW, but hopefully you can imagine some of the benefits of this yourself. The users within the Möbius system consist of administrators, instructors, and students. You have these roles within the system, but you also, within each class, have these roles as well. So someone could be a student at the system level, but it could be given instructor access in a particular course, and you have this flexibility in terms of how you use users within the system. So the Möbius content can be, there's 4 different content types that we have. There are questions, slideshows, math apps, and then flat text pages. And this might seem like kind of a short list, but we'll get into how we can use these to really expand what we're showing. And while you might suspect that some of these are more suited to exposition and some more suited to evaluation, Möbius actually allows you to put pretty well any content in either a lesson or assignment. The only exception is that slideshows are only placed in lessons and are typically used for the exposition pieces. So the question editor and the text editor actually use the same interface. The page you're creating is based in HTML, but has an editor for users that would be similar to other HTML editors or word processors, making it easy to jump in and start creating content. Included in this editor is a robust equation editor with a wide assortment of symbols and operators. The editor also allows users to enter LaTeX math code. LaTeX is a program used for typesetting mathematical documents. It's commonly used by STEM instructors and students at UW. And while users are not required to know or use LaTeX directly, having the support for those who are familiar has been a huge time saver for us. Additionally, because this is essentially a web page, you are able to embed external content into this page, and there are buttons in the toolbar to assist with this as well. If, however, the toolbar does not have the tools that you need and you want to customize things, you also have access to the HTML source, giving you full control over your content and layout. Finally, instructors are able to provide feedback dependent on a user's response to the question. You could choose to show feedback when the student answers incorrectly, or when the student answers correctly, or to always show feedback. Within a lesson, this would be provided immediately after answering the question, but within the assignment context, this feedback could be included after their full attempt or after the due date that you set for the assignment. So in the question editor, there's a tool called Response Area. Adding a response area to your page is what changes it in the Möbius system from a text page to a question. You are also able to have multiple response areas in the same question. There are a variety of types of responses that you can have depending on the complexity of the answer you're asking from the student. Standard multiple choice or true-false questions are available and can have their answers randomized if desired. A numeric answer allows students to enter a number, but can also support arithmetic if desired. So 13 could be written as 1 plus 2 plus 10, and both would be marked the same. Thanks to Maplesoft's mathematical engine, we can go even further than arithmetic and allow students to enter symbolic answers like full mathematical formulas, equations, or expressions. We can use Maple-graded questions as well, giving the author a Maple environment to work with, and this can be extremely useful in situations where there may be more than one right answer. One example I can think of was a question where students were asked to return a set of numbers satisfying a particular property, but there were no restrictions on the numbers themselves. And this is just a sample of the kinds of questions available. In addition to the wide variety of answers that we can ask students to give, one of the strongest features of Möbius questions comes from the ability to create algorithmic questions. And we use this feature extensively at UW. We can write Maple code which will generate random variables. These random variables then can be used to build the question, have an answer dependent on this algorithm, and even generate images on the fly. More often than not, we would primarily use this to randomize what numbers are being used, but the structure of the question would stay the same. However, depending on how complex you want to build your question, you could randomize what information is given to the student and what they need to return as well. An example would be calculating either the present value of an annuity or the future value. These algorithmic questions provide useful functionality within lessons and assignments. Within a lesson context, this can be extremely useful for a student struggling with a particular concept. By creating one question ourselves, we give the student the opportunity to continue trying the problem with different numbers until they have mastered the concept. Within an assignment context, each student attempting this question will receive a slightly different version of the same problem. This is a strong deterrent to students who might be tempted to share answers, which is a concern for many who give assessments online. We can even take this one step further and create what is called an adaptive question. In the example shown on screen, taken from our Chemistry for Engineers course, the student has been asked to find the oxidation state of atoms. The attempt on the left was correct, and the student was immediately taken to the next question. In the attempt on the right, the student was incorrect initially. The student was then led through some additional questions that were not originally shown on the screen, stepping them through the thought process that would eventually get them to the correct answer. While a little more time-intensive to build, this can be incredibly helpful for teaching difficult concepts. It is possible to incorporate this kind of question into an assignment as well, and the grading is extremely flexible so that, if desired, a student could still receive full marks even if they get the initial question wrong. We're going to change gears here and move to our next content item, Slideshows. This is one of the primary tools we're using at UW when creating exposition content. Excuse me. A slideshow feels very much like a video when it is complete, but it is so much more than just that. It takes HTML content, just like we did with questions, but breaks the content into multiple slides and adds the ability to narrate the content. The slideshow editor has a very similar feel to the question editor, with an almost identical toolbar at your disposal, and the same support for entering LaTeX math. Having this consistency between editors contributes to a smoother content creation experience overall. Timing content is incredibly easy. Simply select the content you want to time and drag the starting time of that content on the timeline to where you want it. In the example shown, we timed the final paragraph to come on about 2/3 of the way through this slide, if you look at the image there. Now, at my department, the norm would be to have instructors give their content to a developer in a Word document, PowerPoint, or LaTeX, and it was the developer's responsibility to reproduce their content in the agreed-upon development tool. With a more what you see is what you get kind of editor, like this, some of our instructors have actually started creating content right in Möbius, cutting out that additional step altogether. Audio is recorded for each slide in the slideshow separately. The audio can be recorded right in Möbius or can be imported from your machine if you have a preferred recording environment. It might seem cumbersome to have the audio that divided up, but for users recording directly in Möbius, only having to record a minute of audio at a time is significantly easier than trying to record the entire slideshow in one go. Additionally, if edits have to be made, making edits on a slide-by-slide basis is also a large time save over uploading audio for the entire slideshow for each edit. There are some additional editing tools in the toolbar that are a bit different than your standard editor. The first is blocks. Really, blocks are just div tags in HTML that are pre-styled using CSS. Bear with me if you didn't understand what I just said there. There are 5 different options to choose from by default. For users with a less technical background, this is a quick and easy way to make definitions or theorems pop. In the example shown, I've made some significant changes to the base styling to really emphasize the content, the darker background with the kind of the titles that are really popped out. There's also the aligned environment tool. This essentially builds a table-like environment for you, and we at UW primarily use this to build multi-line equations. Now, you can build a multi-line equation all in one equation if desired, but what the aligned environment allows you to do is time the content in each cell separately quite easily. Thus, as the instructor talks through the content step by step, we can lead the listener's attention to what the instructor is talking about by bringing the equation on piece by piece. Occasionally within a slideshow, you may want to show an animation or demonstration that would not be as effective if done through still images. Möbius slideshows allow you to import video and sync them with the Möbius timeline. To the user, this creates a seamless experience where the video simply flows with the overall slideshow. When it comes to laying out content and establishing the look and feel of your slideshow, Möbius has features in place to assist you. Pre-made templates exist for adding new slides to a slideshow with ready-to-fill areas set up. All templates have a title, as this is used for navigation within the slideshow, but then the various templates can include 1 column or 2 columns, or combinations of those column layouts. Additionally, there are also pre-made themes which involve varying color schemes, different block styling, font sizing, etc. For the majority of our courses at UW, we always start any design with some combination of our pre-made themes. Tweaks can then be made beyond this if required. For the more technical user who may be familiar with HTML, CSS can be provided on a slide-by-slide basis in an area below the main editor, and the code here will be added to any themes already being applied. And then for larger changes, a custom theme can be created that could be used on any slideshow in the course and would also be inherited by child classes. More often than not, setting themes is a discussion that comes up when we're first creating the prototype of the exposition. It's worth noting that themes in CSS can be applied to questions and text pages as well, and we'll often do this within a course to keep a consistent theme throughout. So we talked about questions in their own right, but what you will notice is that the response area tool exists in the slideshow editor as well. This can be used to insert a response area right in your slideshow. Alternatively, you can import an already completed question into your slideshow. Integrating questions right into your exposition is a great way for students to immediately test their knowledge after learning a concept. Slideshows have a pause functionality that automatically stops playback. Pausing the slideshow can be useful on its own when you want a student to take a minute to review something on screen. But when a response area is present and the slideshow is paused, they'll see a "How did I do" button appear. And just like in questions, feedback can be added and can be shown conditionally based on how the student did, or always shown. Students are able to re-enter a new answer if they would like to try again. But when the question present is algorithmic, a try another button will be available that will generate a new version of the question with updated variables. Let's quickly demonstrate how a few of these slideshow features that we've just discussed.
Let's use this slideshow to demonstrate some of the things we've just discussed. To create a new slide, we can use this drop-down menu and choose from a selection of preset templates. The 1 column, 2 columns gives us a title, a content area that spans the whole width, and then 2 columns that are side by side, which can easily be adjusted by just simply dragging the center between them. To show you how to easily change themes, I'll click on the Theme button, and you'll see that I actually already have 4 themes applied to this already. But with a quick switch from color default to color blue, you can see that we can actually change a significant portion of the look and feel of the slideshow itself. This can be very convenient if you're sharing a slideshow with another course that potentially uses a different color theme. To quickly demonstrate what questions look like when they're placed in a slideshow, we'll preview the slideshow now. Jumping ahead to the questions, we can see that if the question does not have an algorithmic section, we do still get a "How did I do" button and a "Continue" button, but we do not get a "Try again" button. It is pretty clear that this has one specific answer that will not change, and that is 1. We can still set up feedback even if it's not an algorithmic question, and this can be provided to the student immediately upon clicking "How did I do?" In the second example of a question here, you'll now note that the "Try Another" button exists. This is because we've added in some randomness to the algorithm. If you keep an eye up here on the sign, you'll see that when we hit "Try Another," we end up getting different numbers in our limit. And the answer is set up as such so that it uses the algorithm that is going on in the background to also algorithmically generate the answer here. Again, we have the feedback explaining how we arrived at this answer.
So I hope that video gave you a picture of how exercises can be integrated directly into the exposition, as well as how we can use the built-in Möbius templates and themes to quickly style our page and jump right into content development. We'll move on to our final content type, math apps. Now at this stage, math apps can't be created directly in Möbius. Instead, they're created in Maple and then imported into Möbius. They are based off of like a Maple worksheet. Some of the ways that we've used this in our courses are using sliders to investigate the features of a function, generating 3D images that can be rotated and fully examined, and allowing users to enter a function of their own, potentially to compare to some base function. This is just a small sampling of what these applications are capable of. So we won't dive into how to create them specifically, but it's good to know that they exist and how they can really be leveraged. On our team, we're really fortunate to have a dedicated Maple specialist who knows Maple well. And understandably, not all institutions would necessarily have this kind of additional support or knowledge of Maple. Fortunately, there are a large collection of materials available on the Maple Cloud. The worksheets and applications found there could potentially be tweaked to work into a math app in Möbius. Now that we've seen the content being developed, we'll talk about how these pieces can be presented within lessons and assignments. So within a lesson, content is organized into sections, and then within each section, we can have one or more items which are stacked vertically. In a course where our primary form of exposition is slideshows, we tend to place a single slideshow per section as shown in the example on the screen. Our opportunities for student exercises and self-assessment are then typically embedded within the slideshow. In courses where content is blended between content types, you might have longer flowing sections with text, embedded content, slideshows, and questions all mixed together, and we'll see an example of this shortly. In the lesson editor itself, already finished content can be easily imported into a section. However, you can also create new content directly from the lesson editor. For small teams or instructors working on their own, this can be a valuable way to quickly produce lessons that are already presentable as soon as the lesson is saved without having to navigate around the Möbius system at all. Just be aware that the content repository for the class may become a little disorganized if you're creating your content directly in here. Let's see these lesson concepts now demonstrated as well.
Let's quickly look over the lesson editor one more time. On the left-hand side, we have our sections listed here with the content items that are currently residing in each. As you can see, we can stack as many items as we want, one on top of the other. The great thing about the lesson editor is that we can actually go into each of these items and edit them right within the lesson editor without having to go back and forth between various areas of the Möbius system. If we create a new section, initially it's empty. But we have several convenient buttons here that let us immediately jump into getting content in this section. I tend to work in the content repository and import from there, but if you wanted to, you could actually create a new question or slideshow directly in the lesson editor. Please note, however, though, that in the content repository, your content may not be organized the way that you want it. Going into the content repository later to organize into folders your newly created content would be a wise idea. If we look at a completed lesson here, in this case they chose to stack quite a number of things one on top of the other. It looks a little bit more like a textbook than just a video presentation or a slideshow. We have some text areas, we have some embedded content from that was made outside of Möbius but brought in to the system. We do have a slideshow here as well, going through some additional examples with some narrated slides. We have our blocks being used here, similar to how the blocks are used in a slideshow to really emphasize content. And right at the end, we have our concept checks, which are, in this case, adaptive questions. These are demonstrated in the main presentation as well, but depending on how I answer these, I may get different questions, which will lead me through how to properly come to the correct answer step by step.
So up to this point, we've focused a lot on exposition and exercises. Let's discuss how evaluation is done through assignments. So assignments are primarily composed of questions, although math apps can be constructed in such a way that they can be graded as well. As mentioned previously, algorithmic questions can be used to give each student a different variation of the same problem. If more variety is desired than one algorithmic question can provide, question groups can be created from which a smaller sample of problems can be pulled for each student. In the example shown, you will see by looking at the navigation pane that there are 3 question groups, and in this case, each group will randomly pull exactly one question from the list given. The 4th and final question shown will be given to all students. From the student's perspective, they will simply see the 3 questions picked for them and the 4th question given to everyone. You might be asking, isn't this a little much? Why would you create this many options when students will only ever see such a small portion? In the example shown, this assignment is from a course quite regularly offered at UW. By creating such a robust assignment, the course can be re-offered from term to term with minimal adjustments having to be made to this assignment. Should the author desire to change questions, questions can quite easily be added or removed from these groups. Assignments can also be set to allow multiple attempts by students. So on an additional attempt, options can even be set which will keep the variation that they got on the first time they went through, or you could even keep correct answers from previous attempts so that they can work through the questions that they got wrong and continue trying the assignment that way. Well, hopefully that gave you a good overview of what Möbius is capable of and how it is designed for the rapid development of content. As a quick recap, before I hand things over to Andrew, I'd like to address or readdress some of the decisions we have made at our department and how we use Möbius in order to efficiently develop content that is still of high quality. First, having instructors enter content directly into Möbius is tremendously useful. Right now, we're still at the stage where instructors are making the call on whether or not they're comfortable with creating their content this way. And we do still provide a small amount of training when we get them started in Möbius if they do choose to do that. The other thing that we like to do is keep customization to a minimum, including the layouts and the CSS behind what's going on. Rather than creating a customized look and feel tailored to each individual course, if we're using the pre-made options, we can focus on the content development rather than on the nitty-gritty details. As mentioned, for many of our courses, slideshows are a great fit for exposition pieces, and the ability to embed questions directly in them is extremely useful for incorporating exercises as well. However, we now have several courses, like the Chemistry for Engineers course that I showed, which have a much more blended approach. Given that that course in particular was very content heavy, the blended approach allowed the team to pick and choose pieces that would benefit from the slideshow-based explanation or the externally developed animations and pieces like that, and the remaining content was able to just be presented as text. Finally, it is worth restating that investing time into well-designed questions at the beginning might be a little bit time-intensive, but can pay large dividends in the long run. A few quick ideas as well that we've come up with for sharing and reusing content. The first is that we're moving towards, at UW, creating parent classes that are going to act as depots for our content items, and then the actual classes that would be offered to students would be created as child classes that draw from the depot in their subject area. In this way, we have all of the content that relates to a specific idea in one convenient location. Another really good tip for sharing and reusing content is not to include the context of the course that you're creating the content for initially, so not using the course code or things like that. This allows you to easily take pieces without having to go in and remove these references to the course that they were originally created for. Extremely useful when we're developing with that in mind. So general pre-made themes allow for easy changes to color and layout. If I haven't done too much extra customization, someone can go in, switch out my color theme for a different color theme that already exists in the Möbius system and have the look and feel changed instantly without any additional work. And it might seem that this is obvious, but keeping your content organized and easy to find is what will determine if it gets reused frequently or not. So in addition to keeping the Möbius's content repository organized, Möbius actually has support for tagging as well, which can be really useful. So I'm going to hand things back over to Andrew to wrap up.
Thanks, Stephen. Thanks for that walkthrough of your use at Möbius, of Möbius at the University of Waterloo. The title of this session was twofold, kind of bringing us back to our beginning. Igniting a global learning transformation and through custom online courseware. Now, global could be taken in a couple of different contexts. Global in the sense that materials could be developed for learners all over the world. Global could also be taken to mean transforming the summative experience of a single learner. Custom online courseware could also be interpreted in a couple of different ways. Custom could mean a unique or tailored set of digital assets or pathway for each student, or custom could refer to the fact that you, as an educator or an instructional designer, now have the complete ability to create rich and engaging content for use by students within your courses, to share across programs, or even to share with colleagues around the world. However you want to define it, though, all of us involved in delivering education today are literally standing on the edge of a transformation, especially as it relates to STEM-based courses, and I truly don't use that term lightly. First, the movement of course materials to the online space represents a bigger and more fundamental shift in education than has ever happened before. Secondly, with new tools now available that have been designed specifically to meet the unique needs and challenges of bringing STEM-based courses online, we all have the ability to deliver a richer, more engaging student learning experience than has ever before been possible. It's exciting possibilities like these that continue to propel our development forward, and we're thrilled to get to work with visionary partners like the University of Waterloo as they seek to continually refine and increase the value of their educational experience for their students, both on campus and around the world. And with that, I will pass back to Andrew, as I think that we still have some time for questions.
All right. Well, thank you to both Steves and the other Andrew for an excellent presentation, and hopefully we can now have a short conversation about some of the queries that are coming in from the audience. We still have about 9 minutes left, so let's get straight to those. I want to turn to first to Steve Farino. I'll address a question coming from Linda in the audience about how students are supervised. And I assume this means both possibly proctoring during assessment and also just making sure that students are staying on track with the coursework. How do you supervise the students?
Thanks for the question. And Linda, feel free to ask a follow-up if I don't capture the meaning of supervise correctly. Thinking of tracking students through content, there's a suite of tools in Möbius that we did not show that allow you to track who has done what question, how many students have viewed what content, and so there's a relatively straightforward mechanism to track in real time who's doing what. Academic integrity is a more difficult problem to solve, and I think we should not delude ourselves that there's some small fraction of our students who will attempt to make their lives easier by any manner of means. What we do at Waterloo is have some of the assessment done online, typically by randomized questions, so it's unlikely that two people working together can simply relay answers to each other. But we also have invigilated exams for all of our math courses.
Okay, all right. Well, for the next question, I want to turn to Stephen Tosh, and I just wanted to find out, assuming that there are points of disagreement between instructors and content creators, and I'm sure that's quite a common thing, what are the most common problems that need to be solved in that area?
Right. So when it comes to content, typically we do always default to the instructor's knowledge on the subject area. Quite often it's going to be those styling issues, things like, do we really need to show all of this text on the screen, or can we keep it in the audio, and small things in terms of how the content's actually being presented. It can be a tricky balance, and I think in a lot of cases we end up defaulting to the instructor's views on things. But I think when you kind of have an overall goal for the institution in terms of how this content is going to be presented, I think better argument, well, not arguments, but better points can be made in terms of like whether our design of courses. So if the disagreement was like over a color, for example, having what I talked about in terms of kind of default themes that we stick to as an institution can help alleviate some of the stress that would come up in some of those arguments and things like that. I hope that kind of gives a bit of insight into that question.
I will add, this is Steve Farino speaking. I'll add one other item. There is a difficulty in keeping faculty members or authors on time, and we use project management to help that, but for those folks who are new to development, they should be aware that hitting deadlines can be a challenge.
Okay. All right, terrific. Well, thank you for adding that. I do. For the next question, I'm going to come to Andrew Rourke first, and then maybe we could shoot over to see if Steve Farino wants to add anything on this one. And Andrew, the question is, a lot of what we've talked about today has been addressed at the higher education level. We do have a question from someone at a high school, in a high school district, who wanted to know, first of all, is the Möbius platform being used for online courses at the high school level? And if so, can you talk a little bit about that? And is there anywhere that someone from a high school could get some examples of how it's working in a high school environment? Can you talk to that a little bit?
Absolutely, yeah. We've got a fantastic example of high school deployment. Let me answer that. Before I give you that answer, let me come back a little bit. At the highest level, what Möbius represents is a courseware development environment. Now, its primary strengths lie along the path of STEM-based courses, but really it can be used in any level of education and in any course. It's a matter of giving you the tools and an environment with which to actually deploy your courseware online. So to that end, can it be used for high school applications? Absolutely. Can it be used for high school STEM applications? Absolutely. And one of the best examples that we have, and we haven't talked about it at all, but it's another project from a completely separate arm of the University of Waterloo. They've got a group called CEMC, which is the Center for Education in Mathematics and Computing. I think I got that right. And they created something called OpenCourseWare. And there were a number of objectives that it was trying to achieve, but just to be brief, what they started with was developing materials for high school students at the grade 12 level. And so they have taken a number of materials that were, some of which existed in previous forms and some of which have been created brand new inside of Möbius. But all these materials have been collected together inside of Möbius. And while the project started at grade 12, it's actually expanding in a bunch of different ways. And again, to be brief, we have lots of examples, and all the materials that are there through that project are open and accessible to anyone. A little difficult for me to actually type this on the screen right now, but if you search for OpenCourseWare CEMC, I believe it's the first result in Google that comes up. Will take you to a site that is actually at courseware.cemc.uwaterloo.ca. And from there, anybody in the world, all these materials are open and accessible, and you can see how that particular group chose to develop and deploy those materials. But I mean, I just brought the page up as I was talking. Advanced functions, pre-calculus, calculus and vectors, a whole raft of really rich materials that they have developed and put up there, the majority of which, like I said, is aimed at high school. So short answer to the question, absolutely applicable.
Okay, no, terrific. Well, thank you very much. And Steve, I'm going to come to you now for probably the final question of the hour, which is, during the beginning of your presentation, you referred to a couple of other platforms and products that you had used. Can you talk about how the Möbius platform differs from other platforms that you've used, particularly as it relates to STEM?
Certainly. One of the basic problems is simply rendering mathematics professionally on the web, and so Möbius does that nicely. I think there are two driving differences for us. One is a mathematical engine, something that understands mathematics from grade school through graduate school, and Möbius has access to the Maple engine. The next is interactivity that's specific to STEM, so that it can draw plots well, that are complicated, that it understands differential equations, those sorts of things. So the interactivity is a really crucial part, both in the ability to manipulate objects and to ask mathematical questions in language that is as close to mathematics as possible.
Okay. All right. Well, thank you for that. I'm afraid that is about all the time that we have left for today. Now, there are some questions that have been coming in from the audience that unfortunately we're not going to be able to get to today, but don't despair. Someone from the Maplesoft team will follow up with you directly to get you some answers. So as we wrap up, I want to thank Dr. Stephen Farino, Stephen Tosh, and Andrew Rolk again for really an excellent presentation today. And I'd also like to thank Maplesoft for its support. And one final reminder, we will be sending out an email to everyone who attended when the recording of the webinar is ready. Thank you all for attending, and this concludes today's webcast. Goodbye.